So how do we do this magical thing called differentiation? That is, how do we take a curve and then create a new curve whose height is equal to the gradient of the old curve? Well, let's go ahead and we'll see how to do that now. Let's imagine we have this function here, which is in red, which is just an original curve. In red, now this curve happens to be f of x equals 0.2x squared, but I've just picked out a random curve for us to work with. Now let's say we want to work out the gradient at that point A on the curve. So what we could do is we could call that point there, we could say, let's say the distance from here to here is a distance x. And then we add on another distance from here to the second point B, which is x plus h. So then we have 2 points. We have a point here x, and we have a point here x plus h, and the distance between them is h. So that means that whenever we work through this function here, this point x is going to map to this point here, which will be f of x, and this point x plus h is going to map to a point f of x plus h. So don't get lost in the nomenclature here. It's telling you something quite simple. We're just saying if this point is 1, then we work through this curve, and that point there will be whatever that value is. If you put 1 into this equation here, it would be 1 squared, which is 1 times 0.2, so that height there would be 0.2. And the same here, this would be another point on the curve, and it would give you another value. But we've just used these values here because it's convenient in order to show you how differentiation works. So we've called that point x, and that point x plus h, so that becomes f of x, and that becomes f of x plus h. So now you see I've also made a note here on the gradient. So I know the gradient at that point A is 0.4. I've already worked it out. Okay, so the gradient at that point there is 0.4, and we're trying to find a way of working out how do we know that's 0.4. So what we can do is we can draw a line between point A and point B. Okay, so that line there between point A and point B, so that line is called a chord. Now what I've done is I've noted the gradient of this chord, and the gradient of this chord at the moment is 1.88. So what we want to do is compare the gradient of this point here and the gradient of the chord, and what we're going to do is move this value B down closer and closer to value A, and we're going to see what happens. So here's a point B. Now if we move this down closer, you can see the chord shape changing. The distance h is getting smaller and smaller, so this length here is getting smaller and smaller, and you'll note that the value of the gradient of the chord is changing as well. You can see it's getting smaller and smaller. Now eventually if we move this value, this point B, closer and closer to point A, then this distance h, it tends towards 0. And you can see here that the length, the gradient of this chord here is tending towards the actual gradient at that point A. So let's keep decreasing, and you can see that value h getting smaller and smaller. So let's say we make h really small, and you can see that h is a really small value. So the point B is coming close to the point A. So now we've got the gradient of the chord is 0.44, and that's close to the gradient at that point A. But what would happen if we were to actually make that distance h equal 0? Well, if this distance h actually equaled 0, then the gradient of the chord would go off to infinity, because the gradient of the chord is just your y distance divided by your x distance. And if this x distance is 0, you're going to have a number y divided by 0. So if you divide anything by 0, you just got a value of infinity. So we cannot let that value of h, that is, we cannot let the distance here equal 0. If we let it equal 0, then we don't get a valid answer for a gradient. But what we can do is we can make it tend to 0. That is, we can make it very, very close to 0, but not actually equaling 0. And the closer we get to this distance equaling 0, then the gradient of this chord tends towards the actual gradient of that point. So by doing this, we've got a method of working out the gradient of a single point on a curve. So let's zoom in and convince ourselves of this graphically. So let's just zoom right into it. And you can hardly see the chord there at all. It almost disappears onto the line. And we just want to bring the value A and B as close together as we can, but we can't actually have them sitting on top of one another. So let's say that is a value of 1.01. Okay, so that's it, really close. So let's have a look and we'll see what the gradient is. Well, we zoom out again. And we can see here that the gradient of that chord is 0.404. So we're getting closer and closer to the actual gradient, which is 0.4. So this is indeed a good method for us to proceed in order to find the gradient of a point on a curve. So let's look at this now mathematically.